The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So remember last time we learned about the cross product of vectors in space. So remember the definition of cross product is in terms of this determinant I hat, j hat, k hat, and then the components of A, A1, A2, A3, and then the components of B. And this is not an actual determinant because these are not numbers, but it's a symbolic notation to remember what the actual formula is. And the actual formula is obtained by expanding the determinant. So we have actually this smaller determinant, A2, A3, B2, B3 times I hat minus determinant of A1, A3, B1, B3 times j hat plus determinant of A1, A2, B1, B2 times k hat. And we also saw a more geometric definition of a cross product. So we've learned that the length of the cross product is equal to the area of the parallelogram with sides A and B. We've also learned that the direction of the cross product is given by taking the direction that's perpendicular to A and B. So in fact, if I draw A and B in a plane, they determine a plane together, then the cross product should go in the direction that's perpendicular to that plane. Now, there's two different possible directions that are perpendicular to a plane, and to decide which one it is, we use the right-hand rule. Which says if you extend your right hand in the direction of vector A, then curve your fingers in the direction of B, then your thumb will go in the direction of the cross product. Okay? So one thing I didn't quite get to say last time is that there are some funny manipulation rules. What are we allowed to do or not do with cross products? So let me tell you right away the most surprising one, maybe if you've never seen it before. It's that A cross B and B cross A are not the same thing. Okay. Why are they not the same thing? Well, one way to see it is to think geometrically. Sure, the parallelogram still has the same area, and it's still in the same plane, so it's still perpendicular to the same plane. But what happens is if you try to apply the right-hand rule but exchanging the rules of A and B, then you will either injure yourself or you will end up pointing in the opposite direction. Okay? So in fact, B cross A and A cross B are opposite of each other. And you can check that on the formula because see, for example, the I component is A2B3 minus A3B2. If you swap the roles of A and B, you will also have to change the signs. Okay, so that's a slightly surprising thing, but you'll see one easily adjusts to it. It just means resist the temptation to write, AB equals BA. Whenever you do that, put a minus sign. Now, in particular, well, what happens if I do A cross A? Well, I will get 0. And there's many ways to see that. One is to use the formula. Also, you can say just that the parallelogram formed by A and A is completely flat, and it has area 0. So that's the 0 vector. Okay. So hopefully you got practice with cross products and computing them in recitation yesterday. Let me just point out one important application of cross product that maybe you haven't seen yet. So let's say that I'm given 3 points in space, and I want to find the equation of a plane that contains them. So say I have P1, P2, P3, 3 points in space. Well, they determine a plane, I mean, at least if they are not aligned. And we would like to find the equation of the plane that they determine. So that means, let's say that we have a point P in space with coordinates x, y, z. Well, the equation of the plane let's say the plane containing P1, P2, and P3. So that means find a condition. We need to find a condition on the coordinates x, y, z telling us whether P is in the plane or not. Okay, so we have several ways of doing that. For example, one thing we could do, let me just backtrack to determinants that we saw last time. So one way to think about it is to consider these vectors P1, P2, P1, P3, and P1, P. Okay? So the question of whether they're all in the same plane is the same as asking ourselves whether the parallelepiped that they form is actually completely flattened. Right? If I try to form a parallelepiped with these 3 sides, well, if P is not in the plane, then it will have some volume. But if P is in the plane, that means that it's actually completely squished. So one possible answer, one way to think of the equation of a plane should be that the determinant of these vectors should be 0. Determinant of P1, P2, P1, P3, and actually let me do it in a different order. It doesn't really matter, but so one possible way to express the condition that P is in the plane is to say that the determinant of these 3 vectors has to be 0. And if I'm given coordinates for these points, I mean, I'm not giving you numbers, but if I gave you numbers, then you would be able to plug these numbers in. So you could compute these 2 vectors explicitly. You would have numbers here. But here, of course, this would depend on x, y, and z. So when you compute the determinant, you get a formula that involves x, y, and z, and you will find that this condition on x, y, z, that's the equation of a plane. Okay, so we're going to see more about that pretty soon. Now let me tell you about a slightly faster way of doing it. Actually, it's not much faster. It's pretty much the same calculation, but it's maybe more enlightening. Oh, let me actually show you the nice color picture that I prepared for this. Okay, so, right. So one thing that's on this picture that I haven't drawn there is the normal vector to the plane. So why is that? Well, let's say that we know how to find a vector that's perpendicular to our plane. Then what does it mean for the point P to be in the plane? Well, it means that the direction, say, from P1 to P has to be perpendicular to this vector n. Okay? So here's another solution. So P is in the plane only when, well, exactly when the vector P1P is perpendicular to n, where n is some vector that's perpendicular to the plane. So that's called a normal vector. Not that the others are abnormal, but Okay. So how do we rephrase this condition? Well, we've learned how to detect whether two vectors are perpendicular to each other using dot product. Okay? Dot product. That's the first lecture. So these two vectors are perpendicular exactly when their dot product is 0. Okay? And so now, concretely, well, if we have a point P1 given to us and say we have been able to compute the vector n, then, well, when we actually compute what happens, here we will have the coordinates x, y, z of a point P, and we'll get some condition on x, y, z. That will be the equation of a plane again. Okay. Now, why are these things the same? Well, before I can tell you that, I should tell you how can we find a normal vector. But maybe you are already starting to see what the method should be, because we know how to find vectors perpendicular to two given vectors. Right? So we know two vectors in that plane, for example, P1, P2, and P1, P3. Actually, I could have used, another permutation of the points, but let's use these. So if I want to find a vector that's perpendicular to both P1, P2, and P1, P3 at the same time, all I have to do is take their cross product. So how do we find this vector that's perpendicular to the plane? Well, the answer is we can just take the cross product P1, P2 cross P1, P3. I should say, well, say that actually you took the points in a different order. You did P1, P3 cross P1, P2. You would get, of course, the opposite vector. That is fine. Any plane has actually infinitely many normal vectors. You can just multiply the normal vector by any constant. You will still get a normal vector. That's absolutely fine. So that's going to be one of the main uses of dot product, C. When we know two vectors in a plane, it lets us find the normal vector to the plane, and that is what we need to find the equation. Now, why is that the same as the answer over there? Well, the condition that we have is that P1P dot n should be 0. And we said n is actually P1, P2 cross P1, P3. So this is what we want to be 0. Now, if you remember stuff from a long time ago, that was Friday, then we've introduced this thing and called it the triple product. Okay, and what we've seen is that the triple product is the same thing as the determinant. So in fact, these two ways of thinking, one saying that the box formed by these three vectors should be flat and have volume 0, and the other one saying that we can find a normal vector and then express the condition that a vector is in the plane if it's perpendicular to the normal vector, they're actually giving us the same formula in the end. Okay. Any quick questions before we move on? Yes? So these two quantities, P1P dot cross product, or the determinant of the three vectors, they're always equal to each other. Okay, they're always the same. And now if a point is not in the plane, then the numerical value will be non-zero. If P is in the plane, it will be 0. Okay, let's move on and talk a bit about matrices. So probably some of you have seen about matrices a little bit in high school, but certainly not all of you. And so anyway, let me just introduce you to a little bit about matrices, just enough for what we'll need later in this class. I should say, if you want to know everything about the secret life of matrices, then you should take 1806 someday. So Okay, so what's going to be our motivation for matrices? Well, in life, a lot of things are related by linear formulas. And even if they are not, maybe sometimes you can approximate them by linear formulas. So often we have linear relations between variables. And for example, well, if we do a change of coordinate systems, so for example, say that we're in space, well, and we have a point, so its coordinates might be, let me call them x1, x2, x3 in my initial coordinate system. But then maybe I need to actually switch to different coordinates to better solve my problem because it's more adapted to other things I will do in my problem. And so I have other coordinate axes. And then in these new coordinates, well, it will have actually different coordinates. Let me call them, say, u1, u2, u3. And then the relation between the old and the new coordinates is going to be by linear formulas. I mean, especially if I choose the same origin. Otherwise, there might be constant terms, which I will not insist on. So let me just give an example. For example, maybe, I don't know. Let's say, for example, u1 could be twice x1 plus 3 times x2 plus 3 times x3. u2 might be 2 times x1 plus 4 times x2 plus 5 times x3. u3 might be x1 plus x2 plus 2x x3. Do not ask me where these numbers come from. I just made them up. Okay, that's just an example of what might happen. So put here your favorite numbers if you want. Okay, so now, in order to express this kind of linear relation, we can use matrices. So a matrix is just a table with numbers in it. And so we can reformulate this in terms of matrix multiplication or matrix product. Okay? So instead of writing this, I will write that the matrix 2, 3, 3, 2, 4, 5, 1, 1, 2 times the vector x1, x2, x3 is equal to u1, u2, u3. Okay, so hopefully you see that there's the same information content on both sides. I just need to explain to you what this way of multiplying tables of numbers means. Well, what it means is really that we'll take exactly these quantities. But let me just say that more symbolically. So maybe this matrix we could call A, and this we could call X, and this we could call capital U, capital X. Then we'll say A times X equals U, which is a lot shorter than that. Of course, I need to tell you what A, X, and U are in terms of their entries for you to get the formula. But it's convenient notation. So what does it mean to do a matrix product? So the entries in product, so I should say so, in the matrix product are obtained by doing the dot product. So let's say we're doing the product AX. So we do a dot product between the rows, dot products, between the rows of A and the columns of X. So maybe I should say here, A is a 3 by 3 matrix. Okay, that just means there's 3 rows and 3 columns. And X is a column vector, which we can think of as a 3 by 1 matrix. It has 3 rows and only 1 column. Okay, so now what can we do? Well, I said we're going to do the dot product between a row of A, 2, 3, 3, and a column of X, X1, X2, X3. Well, that dot product will be 2 times X1 plus 3 times X2 plus 3 times X3. Okay, it's exactly what we want to set U1 equal to. Let's do the second one. I take the second row of A, 2, 4, 5, and I do the dot product with X1, X2, X3. I will get 2 times X1 plus 4 times X2 plus 5 times X3, okay, which is this thing. And same with the third one, 1 times X1 plus 1 times X2 plus 2 times X3. Okay, so that's matrix multiplication. So again, let me maybe restate that more generally. So if I want to find the entries of a product of 2 matrices, A and B, so I'm saying matrices, but they could be, of course, vectors are now a special case of matrices, just by taking a matrix of width 1. Okay, so if I have my matrix A, and I have my matrix B, and then I will get the product AB. Well, let's say, for example, that A, this works in any sizes. So let's say that A is a 3 by 4 matrix. So it has 3 rows, 4 columns. And here I'm not going to give you the values because I'm not going to compute everything. It would take, the rest of the lecture. So, and let's say that B is maybe size 4 by 2. So it has 2 columns and 4 rows. And let's say, for example, that we have the second column is 0, 3, 0, 2. So A times B, I claim, will have, well, the entries should be the dot products between these rows and these columns. Here we have 2 columns. Here we have 3 rows. So we should get, 3 times 2 different possibilities. And so the answer will have size 3 by 2. Okay? And, well, we cannot compute most of them because I didn't give you numbers. But one of them we can compute. We can compute the one that goes here, namely this one, in the second column. So I select the second column of B. And in the first row, so I take the first row of A, and I find, well, 1 times 0, 0. 2 times 3, 6, plus 0 plus 8 should make 14. So this entry here is 14. Okay? So in fact, let me tell you about another way to set it up so that you remember more easily how, what goes where. So one way that you can set it up is you can put A here. You can put B up here. And then you will get the answer here. And if you want to find what goes in a given slot here, then you just look to its left, and you look above it, and you do the dot product between these guys. Okay? So that's, I think, an easy way to remember, first of all, it tells you what the size of the answer will be. The size will be, well, what fits nicely in this box should have the same width as B and the same height as A. And second, it tells you which dot product to compute for each position. Okay, so you just look at what's to the left and what's above the given position. Now, there's a catch. Can we multiply anything by anything? Well, no. Okay, I wouldn't ask the question otherwise. But, but anyway, see, to be able to do this dot product, we need to have the same number of entries here and here. Otherwise, we can't say take this times that plus this times that and so on if we run out of space on one of them before the other. So the condition, and it's kind of important, so let me write it in red. is that the width of A must equal the height of B. Okay, sorry, it's a bit cluttered, but hopefully you can still see what I'm writing. So, okay. But now we know how to multiply matrices. So what does it mean to multiply matrices? I mean, of course, we've seen, on this example, that we can use the matrix to tell us how to transform from x's to u's. And that's an example of multiplication. But now let's say that we have two matrices like that, telling us how to transform from something to something else. What does it mean to multiply them? So I claim that the product AB represents doing first the transformation B, then transformation A. So that's a slightly counterintuitive thing, because we're used to writing things from left to right. Unfortunately, with matrices, the way they're done, you multiply things from right to left. If you think about it, when you write, say, you have two functions f and g, you write f of g of x. It really means you apply first g, then f. So it works the same way as that. Okay, so why is this? Well, if I write ab times x, where x is some vector that I want to transform, it's the same as a times bx. Okay, so this property is called associativity, and it's a good property of well-behaved products, not of cross product, by the way. So matrix product is associative. That means we can actually think of a product a, b, x and multiply them in whichever order we want. We can start with bx or we can start with ab. So now bx means we apply the transformation b to x. And then multiplying by a means we apply the transformation a. So we first apply b, then we apply a. That's the same as applying ab all at once. Okay. So another note of warning is that AB and BA are not the same thing at all. Well, I mean, you probably see that already from this interpretation. It's not the same thing to, convert oranges to bananas than to carrots or vice versa. On the other hand, well, I mean, actually, even worse, this thing might not even be well defined, because, if the width of A equals the height of B, we can do this product. But we don't necessarily, I mean, it's not clear that the width of B will equal the height of A, which is what we would need for that one. Okay, so, the size condition to be able to do the product might not make sense, actually. Maybe one of them doesn't even make sense. Even if they both make sense, they're usually completely different things. Okay. The next thing I need to tell you is something called the identity matrix. Well, the identity matrix is the matrix that does nothing. Okay, so what does it mean to do nothing? I don't mean the matrix 0. The matrix 0 would take x and would always give you back 0. That's not a very interesting transformation. What I mean is the guy that takes x and gives you x again. So it satisfies property I, so it's called I, and it has a property that ix equals x for all x. So it's the transformation from something to itself. It's the obvious transformation called the identity transformation. So how do we write that as a matrix? Well, so actually there's an identity for each size, because, of course, depending on whether x has 2 entries or 10 entries, the matrix I needs to have a different size. So, for example, the identity matrix of size 3 by 3 has entries 1, 1, 1 on the diagonal and zeros everywhere else. Okay, let's check. If we multiply this with a vector, well, okay, maybe I should do that on a separate board. But so start thinking about it. What happens when I multiply this with a vector x? Okay, so let's say I multiply the matrix I with a vector x1, x2, x3. Well, what will be the first entry? It will be the dot product between 1, 0, 0 and x1, x2, x3. If you want, this vector is I hat. Okay, so if you do the dot product with I hat, you will get the x component. You will get the first component that will be x1. 1 times x1 plus 0, 0. Similarly here, if I do the dot product, I get 0 plus x2 plus 0. I get x2, and here I get x3. Okay, it works. Same thing if I put here a matrix, I will get back the same matrix. Now, of course, okay, so in general, the identity matrix in size n by n, so it's an n by n thing with ones on the diagonal and zeros everywhere else. Okay, you just put 1 at every diagonal position and 0 elsewhere. And then you can see if you multiply that by a vector, you will get the same vector back. Okay. Oh. Okay. Let me give you another example of a matrix. Let's say that in the plane, we look at the transformation that does rotation by 90 degrees. Let's say counterclockwise. So I claim that this is given by the matrix 0, 1, minus 1, 0. So let's try to see why that is the case. Well, if I do r times I hat, so if I apply that to the first vector, I hat, so that means, okay, I hat will be 1, 0. This product, well, here you will get 0, and then you will get 1. You get j hat. Okay, so this thing sends I hat to j hat. What about j hat? Well, you get negative 1, and then you get 0. So that's minus I hat. So j is sent towards here. And in general, if you apply it to a vector with coordinates xy, with components xy, then you will get back minus yx, which is the formula we've seen for rotating a vector by 90 degrees. So it seems to do what we want. By the way, I should point out, so the columns in this matrix represent what happens to each basis vector, to the vectors I and j. See, this guy here is exactly what we get when we multiply r by I. And when we multiply R by J, we get this guy here. So what's interesting about this matrix? Well, we can do computations with matrices in ways that are easier than writing coordinate change formulas. For example, if you compute R squared, so if you multiply R with itself, well, I let you do it as an exercise, but you will find that you get minus 1, minus 1, 0, 0. So that's minus the identity matrix. Why is that? Well, if I rotate something by 90 degrees, and then I rotate by 90 degrees again, then I will rotate by 180 degrees. That means I will actually just go to the opposite point around the origin. So I will take xy to minus x minus y. Okay? And if I applied R 4 times, R to the 4 would be identity. Okay, questions? Yes?
When you came out for R equals that matrix, is that like the definition of R, or is that just?
That's a very good question. So how did I come up with this R? Well, secretly, I worked pretty hard to find what are the entries that would tell me how to rotate something by 90 degrees counterclockwise. So remember, I should have said, what we saw, I think, last time or in the first lecture, is that to rotate a vector by 90 degrees, we should change xy to minus yx. Okay? And so now I'm trying to express this transformation as a matrix. And if you work out, how these guys, so maybe you want to call these guys u and v, and if you write u equals 0x minus 1y, 0x minus 1y, and then v equals 1x plus 0y, 1x plus 0y. Okay, so that's how I would find it. Here, actually, I just gave it to you, ready-made. So you didn't really see how I found it. But, you will see more about rotations on the problem set. So you're going to see more about these things. Okay. So next, I need to tell you how to invert matrices. So what's the point of matrices? It's that it gives us a nice way to think about these changes of variables. And in particular, if we know how to express u in terms of x, maybe we'd like to know how to express x in terms of u. Well, we can do that because we've learned how to solve linear systems like this. Okay? So in principle, we could start working, substituting, and so on, to find formulas for the x1, x2, x3 as functions of u1, u2, u3. And the relation will be, again, a linear relation. It will, again, be given by a matrix. Well, what's that matrix? It's the inverse transformation. So it's the inverse of the matrix A. So we're going to learn how to find the inverse of a matrix directly. Okay. So the inverse of A, by definition, it's a matrix M with a property that if I multiply A by M, then I get identity. And if I multiply M by A, I also get identity. If the two properties are equivalent. So that means, if I apply first the transformation A, then the transformation M, I undo the transformation A, and vice versa. These two transformations are the opposite of each other. Well, I should say the inverse of each other. Okay? So for this to make sense, we need A must be a square matrix. Okay, so it must have size n by n. It can be any size, but it must be the same number of rows as columns. And it's a general fact that, you will see more in detail in linear algebra if you take it. So let's just admit that. So the matrix M we will denote by A inverse, like this. Okay? And then what is it good for? Well, for example, the solution to a linear system. So what's a linear system in our new language? It's a matrix times some unknown vector x equals some known vector b. Well, how do we solve that? We just compute x equals A inverse b. Why does that work? How do I get from here to here? And let's be careful. Oh. Okay, well, I'm going to reuse this matrix, but I'm going to erase it nonetheless. I'll just rewrite it. So I'm saying if AX equals B, then let's multiply both sides by A inverse. A inverse times AX is A inverse B. And then, well, A inverse times A is identity. So I get X equals A inverse B. Okay, that's how I solved my system of equations. So if you have a calculator that can invert matrices, then you can solve linear systems very quickly. Now, we should still learn how to compute these things. Yes? How do I know that A inverse will be on the left of B and not after it? Well, it's exactly in this derivation. So if you're ever not sure, then just reproduce this calculation. See, I mean, to get from here to here, what I did is I multiplied things on the left by A inverse. And then these guys simplify. If I had put A inverse on the right, I would have AX A inverse, which might not make sense. And even if it makes sense, it doesn't simplify. So, I mean, the basic rule is, you have to multiply by A inverse on the left so that it cancels with this A that's on the left. That's correct. So, and in our usual way of dealing with matrices, where the vectors are column vectors, I mean, it's just something to remember that if you have a square matrix times a column vector, I mean, the product that makes sense is with the matrix on the left, the vector on the right. The other one just doesn't work. It's not sized. You cannot take x times A if A and x, if A is a square matrix and x is a column vector, this product makes sense. The other one doesn't make sense. It's not the right size. Okay. So what we need to do is to learn how to invert a matrix. And it's useful to know first for your general knowledge, and second because actually it's actually useful later for things we'll see in this class. So in particular on the exam, you will need to know how to invert a matrix by hand. So I should say this formula is actually good for small matrices, 3 by 3, 4 by 4. It's not good at all if you have a matrix of size 1,000 by 1,000. So in computer software, actually for small matrices, they do this. For larger matrices, they use other algorithms. But let's just see how we do it. So I'm going to do it. Okay, so first of all, I will give you the final answer. And of course, for that, I will need to explain what the answer means. So we'll have to compute something called the adjoint matrix. And I will tell you how to do that. And then we'll divide by the determinant of A. So how do we get to the adjoint matrix? So let's go through the steps on a 3 by 3 example. The steps are the same no matter what the size is, but let's do 3 by 3. So let's say that I'm giving you the matrix A. Well, let's say it's the same as earlier, the one that I erased. So that was the one relating our x's and our u's. So the first thing I want to do is find what's called the minors. So what's a minor? Well, it's a slightly smaller determinant. We've already seen them without calling them that way. So for example, so the matrix of minors will have again the same size. Okay? Let's say we want this entry. Then we just delete this row and this column. Sorry, this row and this column, and we are left with a 2 by 2 determinant. Okay? So here we'll put the determinant 4, 5, 1, 2, which is 4 times 2, 8, minus 5, 3. Let's do the next one. So for this entry, I delete this row and this column. I'm left with 2, 5, 1, 2. Determinant will be 2 times 2 minus 5 is negative 1. Then minus 2. Then I get to the second row. So I get to this entry. Well, to find the minor here, I will delete this row and this column, and I'm left with 3, 3, 1, 2. 3 times 2 minus 3 is 3. And let me just cheat and give you the others. I mean, I think I've shown you that I can do them, okay? So let's just explain the last one again. The last one, this 2, so to find the minor here, I delete this column and this row, and I take this determinant, 2 times 4 minus 2 times 3. Okay, so it's the same kind of manipulation that we've seen when we've taken determinants and cross products. Okay, step 2, we go to another matrix that's called cofactors. So the cofactors are pretty much the same thing as the minors, except the signs are slightly different. Okay, so what we do is we flip signs according to a checkerboard diagram. So you start with a plus in the upper left corner, and you alternate pluses and minuses. Okay, so the rule is if there's a plus somewhere, then there's a minus next to it and below it. And then below a minus or to the right of a minus, there's a plus. Okay, so that's what it looks in size 3 by 3. So what do I mean by that? So I don't mean, make this positive, make this negative, and so on. That's not what I mean. What I mean is if there's a plus, that means leave it alone. Okay? We don't do anything to it. If there's a minus, that means we flip the sign. Okay, so here we get, 3, then 1, minus 2, minus 3, 1, plus 1. Maybe I'll put pluses just to emphasize. 3, minus 4, and 2. Okay? That step is pretty easy. I mean, the only hard step in terms of calculations is this one, because you have to compute all of these 2 by 2 determinants. By the way, I mean, this minus sign here, see, it's actually very related to the way in which, when we do a cross product, we have a minus sign for the second entry. Okay, we're almost done. Third step is to transpose. So what does it mean to transpose? It means you read the rows of your matrix and you write that as columns, or vice versa. Okay, so let me just say we switch rows and columns. So what do we get? Well, let's just read it horizontally and write it vertically. We read 3, 1, minus 2. 3, 1, minus 2. Then we read minus 3, 1, 1. Minus 3, 1, 1. Then 3, minus 4, 2. 3, minus 4, 2. Okay? That's pretty easy. And we're almost done. The last step, so what we get here is this is the adjoint matrix. So the fourth and last step is to divide by the determinant of A. Okay? So here we have to compute the determinant. 2, 3, 3. So I should say determinant of A, okay, not the determinant of this guy. So 2, 3, 3, 2, 4, 5, 1, 1, 2. Well, I'll let you check my computation. I found that it's equal to 3. Okay, so the final answer is that A inverse is 1/3 of the matrix we got there. 3 minus 3, 3, 1, 1 minus 4 minus 2, 1, 2. Okay, and now, so that tells us, remember A told us how to find the u's in terms of the x's. This one tells us now how to find the x's in terms of the u's. If you multiply u1, u2, u3 by this, you get back x1, x2, x3. It also tells you how to solve the linear system A times x equals something. Okay, that's the end for today.